Hello, my name is Bridget Lefebvre, and my project is on X-ray diffraction for the analysis of perovskite crystals, degradation, and solar cells. While there are many crystal structures used to create solar cells, the structure of perovskite crystals that are of interest for use in solar cells and that I will be focusing on is the cubic ABX3 structure. The ABX3 structure consists of cations at the A site, which is shown here in pink, as well as cations at the B site, shown in purple, and anions at the X sites, shown in green. Of the perovskites that are investigated for photovoltaics and solar cells, B is normally a lead, A is a small organic cation such as methylammonium or formimindium, or a relatively large inorganic cation such as cesium, while the X sites are a halide such as iodine, bromine, or chloride. These ABX3 perovskite crystals are desirable for solar cells because the structure has both high charge carrier mobility and lifetime, which allows electrons and holes generated by light to create current rather than heat that would dissipate out of the cell. The perovskite crystals are also much cheaper to manufacture than the currently preferred single crystal silicon solar cells, as perovskite solar cells can be constructed through deposition or spin coating. When we are creating perovskites for solar cells, the use of methylammonium or formimindium has been found to be the most stable A-site cation. Recent research has also found some mixtures of both methylammonium and formimindium to be stable as well. As you can see in the diagram, the common lead iodine solution, with lead being the cation and iodine being the anion, is mixed with either methylammonium, formimindium, or both to create the crystal structure. So you can see in the second step that methylammonium lead iodide perovskite forms an undesirable tetragonal structure at room temperature, but when those crystals are heated, the phase transitions to the desirable cubic structure. The addition of formimindium makes the cubic structure more stable at close to room temperature, but it is observed that factors can degrade them more quickly as well. The addition of cesium as a third cation to replace some methylammonium or formimindium has shown promise because of cesium's larger atomic radius. Because only the cubic structure of ABX3 perovskites are photovoltaic, the transition of crystals to the tetragonal ABX3 structure renders a perovskite solar cell unusable. So the tetragonal and cubic phases are important. The tetragonal and cubic phases are called yellow and black phases respectively because the non-photovoltaic yellow phase is yellow and the cubic structure is black. Both methylammonium and formimindium perovskites are unstable and degrade to yellow phase perovskite crystals from a multitude of factors. These include the temperature, moisture, and light that the solar cell is exposed to, and unfortunately, solar cells in commercial use are exposed to degrading levels of all three. As is seen in the diagrams on the right, the cubic structure of ruthenium lead iodide perovskite at the top has high intensity peaks, while the tetragonal structure has more and lower intensity peaks. The X-ray diffraction pattern on the left shows the theoretical intensities of the yellow and black phase formimindium lead iodide structures. Because the crystal structure of perovskite is so crucial to the success of these solar cells, X-ray diffraction analysis is used to analyze the crystal structures of many solutions being explored. Because of how quickly perovskite crystals degrade, perovskite solar cells are not ready for large-scale use in energy capture. Using X-ray diffraction to determine the shifts in crystal structures due to both the chosen solutions and external factors can help push perovskite crystals to being viable solar cells. Powder X-ray diffraction is used in creating perovskite layer crystals through spin coating layers or deposition of layers, and then these crystals are ground into a powder to create the sample. Single crystal diffraction is a less common method, but has been used in some characterization. And some perovskite solar cells use thin films of perovskite as the photovoltaic layer, and these films are characterized using Greason incidence wide-angle X-ray scattering. However, we are mostly going to be focused on the use of powder diffraction. X-ray diffraction analysis is most helpful in determining to what extent a perovskite crystal has degraded, especially between the yellow and black phases. X-ray analysis has been useful in determining the temperature-dependent phase shifts in perovskite material, as well as how moisture degrades the perovskites and discovering defects in perovskite samples. So when we're looking at the temperature degradation of a perovskite, the methylammonium lead iodide perovskite has a tetragonal structure at room temperature, which is the yellow structure. However, it shifts to cubic structures at higher temperatures. In order to determine the temperature that the shift occurred, Jacobson et al. Ran experiments and used temperature-dependent X-ray diffraction data and compared it to the simulated data of the tetragonal and cubic phases to determine the temperature that the shift occurs at. So you can see here the expected X-ray diffraction patterns for the room temperature tetragonal structure is in orange, and then the higher temperature cubic structure is in blue. You can see that the intensity of the cubic structure peaks are lower than the tetragonal, and that some of the cubic structure peaks have shifted to the left. In the first temperature-dependent X-ray diffraction scan from Jacobson et al., 15 peaks were used to identify the methylammonium lead iodide perovskite. These peaks were consistent with the theoretical peaks of the yellow phase of the perovskite, and the changes in these peaks were observed in the temperature samples that were taken. As you can see here, the temperature-dependent X-ray diffraction was measured. The angles were between 12 and 60 degrees, and the temperatures were between 35 degrees Celsius to 97 degrees Celsius. Each graph focuses on a different one of the 15 characteristic peaks, and each line is a different temperature peak, with the lower temperatures at the base and the higher temperatures going up the y-axis. You can see in many of the graphs the leftward shift that you would expect from the theoretical X-ray diffraction patterns shown before. And the greater shifts are obvious, as well as the merging of the two smaller peaks in graphs 8 and 10 that show the transition from tetragonal to cubic structure methylammonium lead iodide crystals occurred about midway through the temperature-dependent measurements. This research confirmed that the phase shift from tetragonal to cubic phase occurred in methylammonium lead iodide perovskite. Using the X-ray diffraction patterns in the Bragg equation, the d-spacing of the crystals at each temperature were measured and calculated and compared to the dimensions of the tetragonal and cubic phases, and it was found that the phase shift begins when the methylammonium lead iodide crystals were heated to 54 degrees Celsius. This was important because this temperature is considered within operating conditions for a solar cell in direct sunlight. However, the natural temperature cycle in a day would cause a pure methylammonium lead iodide perovskite to transition between the yellow and black phases. They know it would continue transitioning because after collecting the temperature-dependent data, the sample was left to cool back to room temperature, and a new scan was collected and showed that the transition is reversible. However, the effect of repeated transition for the decade-long lifespan of a solar cell is still not well understood. And so this higher transition to cubic structure is undesirable and still needs a solution. As well as the temperature-dependent phase transition, X-ray diffraction has been used to see how moisture affects the degradation of solar cells. The X-ray diffraction analysis was used on methylammonium lead iodide perovskite solar cells exposed to moisture. and showed that moisture had distinct effects in both the absorption spectra and morphology of these crystals. To figure out what was happening in the crystal structure, X-ray diffraction data of lead iodide, which is the black line, methylammonium lead iodide, which is the red line, and a synthesized methylonium lead iodide hydrate, which is the pink line, were taken, and then these samples of the methylonium lead iodide perovskites were exposed to moisture. The methylammonium lead iodide sample kept at 50% relative humidity did not degrade. However, the sample kept at 90% relative humidity showed peaks at 7.93 degrees, 8.42 degrees, 10.46 degrees, and 16.01 degrees, which are characteristic of the hydrate, which was shown in pink. But there are still peaks visible at 13.98 and 28.32 degrees, which is most likely some crystalline methylonium lead iodide that remained in the film and did not degrade. This research did not show a phase shift due to moisture, but the formation of a hydrate when exposed to high humidity. However, the low humidity did not show degradation. The use of X-ray diffraction analysis also allows for the detection of defects in a sample. So for example, this X-ray diffraction analysis shows the experimental data from a drop-coated methylammonium lead iodide perovskite, as well as the simulated patterns for the tetragonal and cubic structures shown in orange and white. However, at about 13 degrees, there is a peak that is characteristic of lead iodide, which is the solution that methylammonium is added to create the perovskite crystals, which shows that the manufacturing of the sample was flawed and did not result in a complete perovskite layer. While XRD analysis is effective for characterizing perovskite crystals, there are some downsides to using XRD. For example, once the sample of perovskite is used for powder diffraction, the sample's power conversion efficiency can't be measured to determine its efficiency after degradation. That kind of information can only be taken before, if it is taken at all. Another issue is that while XRD is effective at determining phase transitions, the exact structure had to be measured by neutron diffraction. So, of the other characterization methods, neutron powder diffraction is important. As stated before, it was used to determine the exact structure and measurements of the perovskite. The theoretical X-ray diffraction patterns that were used in other research was derived from the measurements taken from the neutron powder diffraction. The figure on the left shows the orthorhombic, tetragonal, and cubic structures that were derived from the neutron powder diffraction. The orthorhombic structure is not of interest for solar cell research because it's formed when the perovskite is cooled and has no photovoltaic properties, so it would not appear at room temperature and is not of use in a solar cell. The right-hand figure shows the intensity as temperature increases and shows distinct shifts at the dotted lines for each phase. And this intensity data was used to find the exact structure of the perovskite, which is shown in these diagrams. The orthorhombic structure was found to be most stable at 100 degrees Kelvin and was found to have an average lead iodide lead bond length of 154.5 degrees. This is due to the iodine atoms in one square face moving towards the nitrogen hydrogen end of the methylammonium cation and away from the carbon end. The tetragonal structure was found to be stable at 180 degrees Kelvin, and this was used to create the model. The lead iodide lead bonds in the tetragonal structure have an average of 165.3 degrees, which makes for a much less skewed structure than in the orthorhombic structure. The cubic structure was found at 352 degrees Kelvin, and in the cubic structure, all lead iodide lead angles become 180 degrees, giving it its cubic structure. So the transition from orthorhombic to tetragonal to cubic creates these three distinct structures. So overall, X-ray diffraction is essential for researchers to determine the phases of perovskites in photovoltaic applications. Thank you for listening.